In electrical wiring, especially when dealing with 220-volt single-phase systems, adhering to standardized color codes is crucial for safety and proper identification. The color orange is designated for the high-leg or the ungrounded conductor when dealing with specific voltage configurations. However, in your case, with a 220-volt single-phase supply, it is important to understand that the standard color code for the ungrounded conductors, which are the wires leading from the main disconnect to the line-side devices in the panel, typically involves different colors. The National Electrical Code, or NEC, outlines these standards. For a 220-volt single-phase system derived from a 240-volt system, which is common in many residential and light commercial applications, the typical colors for the ungrounded conductors are black and red. The grounded conductor, or neutral, is white or gray, and the equipment grounding conductor is green or bare copper. The use of orange is specifically reserved for the high-leg in a three-phase delta system. This system is not very common and requires very specific attention for the B-phase wire. The phase with the higher voltage to neutral is colored orange. It's crucial not to confuse this with a standard 220-volt single-phase setup. In your situation, you're feeding 220-volt single-phase to two devices from the main disconnect. The recommended practice is to use black and red wires for the ungrounded conductors. Connect one 120-volt leg to the first device using black wire and the other 120-volt leg to the second device using red wire. Keep in mind that 220 volts is a voltage potential between the two 120-volt legs. If these devices also require a neutral, which is unlikely for most 220-volt appliances, then use a white or gray wire. Also, connect a green or bare copper wire to ground the chassis of the devices, if required. Now let's delve deeper into the National Electrical Code, or NEC, and wiring standards. Firstly, always consult the latest edition of the NEC for the most up-to-date regulations. Secondly, local codes may have additional requirements or variations, so it's important to check with your local electrical inspector. 3. Proper wire sizing is crucial. Use a wire gauge appropriate for the amperage of the circuit to prevent overheating and potential fire hazards. NEC Table 310.15 provides guidance on ampacity ratings for various wire sizes and insulation types. 4. Ensure all connections are properly tightened and secure. Loose connections can cause arcing, which can also lead to overheating and fire. 5. Label all wires and connections clearly to facilitate future troubleshooting and maintenance. Wire markers and labels are readily available for this purpose. 6. Use appropriate overcurrent protection devices, such as circuit breakers or fuses, to protect the wiring and equipment from overloads and short circuits. The size of the overcurrent protection device should match the ampacity of the wiring. 7. When working with electrical panels, always de-energize the circuit before making any connections or modifications. Use a voltage tester to verify that the circuit is de-energized. 8. Wear appropriate personal protective equipment, or PPE, such as safety glasses and insulated gloves, when working with electrical systems. 9. If you're not comfortable working with electricity, it's always best to hire a qualified electrician to perform the work. 10. Consider the specific requirements of the devices you're connecting. Some devices may require dedicated circuits or special wiring configurations. The manufacturer's instructions should provide guidance on these requirements. The grounding system is an essential part of the electrical system that is designed to protect from dangerous electrical shock. The neutral, also known as the grounded conductor, carries current back to the source. The equipment ground is connected to the chassis and metallic parts of electrical equipment. It provides a low impedance path for fault current to return to the source, causing the overcurrent protection device to trip and de-energize the circuit. This protects people from electric shock and prevents damage to equipment. Be sure to connect all equipment grounds to the grounding busbar in the electrical panel. Also, be sure that the grounding busbar is properly connected to the grounding electrode system, which typically consists of ground rods or metal water pipe. The proper installation of the grounding system is critical for safety. Always follow NEC guidelines when installing grounding electrodes and connecting grounding conductors. Also, when dealing with 220-volt circuits, GFCI protection is not always required, but it may be beneficial in certain applications, such as in bathrooms or outdoors. GFCI, or ground fault circuit interrupter, devices detect ground faults and quickly de-energize the circuit to prevent electric shock. Check your local codes and NEC requirements to determine if GFCI protection is required for your specific application. For example, if you are supplying a hot tub or spa with a 220-volt circuit, GFCI protection is almost always required. Similarly, circuits that supply outdoor receptacles or equipment that is likely to get wet should also be GFCI protected. Let's talk more about the high-leg delta system where orange wire is used. The high-leg delta system is a three-phase power distribution system that is commonly used in industrial and commercial applications. It has one phase that has a higher voltage to neutral than the other two phases. This phase is typically identified with an orange wire. The high leg is created by center tapping one of the transformer windings in a delta-connected transformer bank. This center tap is grounded, creating a neutral point. The voltage from the high leg to the neutral is typically 208 volts, while the voltage from the other two phases to neutral is 120 volts. Because the voltage from the high leg to neutral is higher than the voltage from the other two phases to neutral, it is important to identify the high leg with an orange wire. This helps to prevent accidental connections to the high leg, which could damage equipment or cause electric shock. The high leg delta system is not as common as the Y system. This is because the high leg can be confusing and dangerous if not properly identified. However, a high leg delta system can be a cost-effective way to provide both single-phase and three-phase power to a facility. Finally, remember that electrical work can be dangerous, and it is always important to take precautions to protect yourself from electric shock. If you are not comfortable working with electricity, it is best to hire a qualified electrician to perform the work. If you are working with electricity, always de-energize the circuit before making any connections or modifications. Use a voltage tester to verify that the circuit is de-energized. Wear appropriate personal protective equipment, such as safety glasses and insulated gloves. Follow all applicable codes and regulations. Electrical safety is a serious matter, and it is important to take it seriously. In summary, while orange is used for the high leg in three-phase delta systems, black and red are the standard colors for ungrounded conductors in a 220-volt single-phase system. Always consult the NEC and local codes, use proper wire sizing and overcurrent protection, and prioritize safety when working with electrical systems. If in doubt, consult a qualified electrician.